Give kind of a brief overview of wind and solar and such. And then at the end, I'm going to talk about the models because all the new, I could probably say all of the new wind farm or new generators you're putting in transient stability models, they're all these things. So I'm going to get and talk mostly about the models at the end, but just kind of briefly introduce what renewable things are. So we've talked about hydro, we've talked about solar and steam. So here we're going to talk about the renewable plants. I think people are finding, this isn't something Power World can help you with, but EMTP type studies. Are you guys doing those on wind farms here yet? Okay, I know ERCOT has started doing them. The reason it's funny is I do presentations, not on this, but when I introduce subsynchronous resonance, I used to say, and people figured that out in 1960, and we don't worry too much about that anymore. Because they broke shafts on generators in the 60s, and they figured out how coal plants could have this resonance between the electrical and mechanical. And so I said, but we don't worry about that anymore. But then ERCOT was having a lot of trouble, probably about 5 to 10 years ago, with wind turbines just tripping. And what was going on is the inverters, it's just a piece of software. And you tune these PI loops and everything to design your control system. And they were creating resonance in that control system with the electric system. And if they ran a transient stability simulation, everything looked fine. And it wasn't until they went, after the turbines kept tripping, they went in and started modeling all the EMTP stuff. So that might be on your horizon someday.
How'd they get them to share the detailed models? They're usually pretty tight about those.
I assume they just paid them lots of money. I don't know exactly. All right, so you guys all know this. Wind is growing a lot. This is the new installed wind each year, and it's growing. And this is true. I mean, if you look at offshore installations as well, are starting to come up. But really, much of the world is adding this stuff. So here's the growth in the U.S. wind. You can tell we made these slides in about 2018 because it stops them at that point. I always like looking at these. The colors are showing you like the first, second, third, and fourth quarter. And the fourth quarter is like all the big things because they're trying to get them in the ground before the tax credit might expire and they don't know for sure. So I always imagine 2 trucks and 2 guys with a shovel going, okay, we started. But that's what's going on here. So it is growing, definitely growing. Here's cumulative wind. Wow. So this is the wind installed by state. So megawatts, yeah. You know, if you look at this, it's funny because you think of Texas as this oil land, oil and gas, but it has been wind. They've invested a lot in transmission so that they can have all the wind farms out here and get them over to the cities. So here's the wind
across nothing, you know.
What was that?
It's not like us where we got to go through beautiful country with our.
Fair enough.
They're going across the
West
middle
Texas
of nowhere.
And they have one state commission to talk to.
Yeah, and so, but they held all that wind back, right? They held it all back, and then it was like almost all of it came on at one time.
Yeah, well, they built the transmission to allow it.
Yeah.
It's funny, our other customers at Power World our big customers are companies like you and little companies that buy and sell energy futures and credits and participate in markets. So those customers actually really didn't like Texas after they built all that transmission because the prices all dropped and kind of leveled out and there was no. So they're like, ah.
Are they pretty much homogenous and they're excited? And they're wind turbine types since they're pretty much both at the same time?
I don't know. Yeah, I don't know. I'm going to guess they're all type 3 and 4 for sure, but I don't know.
I think that's right.
This is a slide, states are driving this. There are lots of you guys know this, Washington, Oregon have rules. Washington says you must close all your coal plants, right? Is that happening?
Yes.
Yes.
It is,
2025.
Yeah, so, your gas plants also?
By 2045, you
Oh.
can't buy from a gas plant if you're
So we're gonna be powering the state with sticks and stones.
Sticks and stones. All right, wind resources. Yeah, part of probably what who's funding your big project to merge all the grids? Who's that? SPP. This is probably part of the reason. Is because if you're gonna build a lot of wind, then this is where it's at, but this is between the interconnects. So you're gonna need to get the power both directions if we did a huge amount of that. There's Texas, so again, all the wind in Texas tends to be up in West Texas. And one of the funny things in Texas, a lot of the wind in Texas is in the Eastern Interconnect, because it's up here. All right, wind turbines, they're getting really, really big. So these are Tom's slides, and I like them because this is the Washington Monument. The new turbines they're putting in, that's how big they are. They're bigger than the Washington Monument. Here's the Statue of Liberty. So when they drive by you on the interstate, and you're like, that's like a quarter the length of a football field with a blade going by. They're very, very big. The advantage of that is they get up high enough. When you're down low on the ground, the wind speed varies a lot. If you get higher and higher up, it's a little bit more consistent.
The other advantage is it kills a lot more birds.
No. The bigger it gets, the slower the turbine spins, so the bird can
Dodge it.
dodge it, right?
That's untrue.
That's not true. It just breaks the bones. See, they don't die till a week later.
But the RPM is the actual velocity of the like tip speed.
The tip speed is really fast.
It is? Okay.
Well, in physics, right?
Yeah, no, it makes sense.
And so it's killing birds, like bags and bags of birds.
But only
They do. They bag them up. They have to count them.
All right, I want to move on from the bird talk.
Come on, let's pull up some slides.
All right, one thing to know about wind, this is true in your car too, but the amount of energy in wind goes up, I think it says the cube of wind speed. So it goes up higher and higher, and at some point, the blade's going to spin too fast, so you're going to basically feather the blade so you're not catching so much wind. So they're designed to catch as much wind as possible. So these are some plots on some wind machines.
They also put more resistance to slow it down.
Do they put mechanical resistance in?
Used to. Now the blade.
Yeah, I would assume the blades just rotate to kind of like not catch it. You're like this, and then go, oh no, I don't want the wind. All right, wind farms are made up of collector systems. You guys know this. In a power system tool like ours, you'll tend to model this as one generator or maybe a couple, and then have an equivalent of the collector system. You guys don't have cows out by your wind turbines, but West Texas probably does.
Yeah, we do.
Do you have cows?
We have cows.
Tons. Okay.
Most of ours are out in the east shores. So
Okay.
dryland.
All right. That makes sense. All right. Another thing that's changing is a very good place to build wind turbines is out on the ocean because,
So there's no birds there.
well, there's no birds there. And the wind is more consistent out there. So as long as there aren't people with expensive homes here complaining, you can put them out in the ocean. That is starting to happen. Here's a picture of England and Denmark. They have big wind installations out in the middle of the sea. All right. There are 4 general types of wind turbines. Type 1 wind turbines, it's just an induction machine, like the loads I talked about yesterday. The problem with an induction machine is you have no voltage control whatsoever. Whatever the P output is, you do a bunch of math, and the Q is just a function of the voltage and P. So you have no ability to control voltage. Type 2 wind turbines add in a rotor resistance and give you some ability to control voltage. Sounds like you guys have quite a lot of these. They're old. I'm going to guess they're 15 years or older. So nobody's allowed to install these at either 1s or 2s anymore, because they just don't provide enough control for the grid itself.
I thought they had small caps inside to,
In the type 2s?
even the ones I thought. Maybe the ones just
Well,
have external.
correct. They would just have external caps to probably just to keep it at zero, at power factor of 1 or something. All right, type 3 wind turbines. This is where it's a little outside of my depth, but basically they're taking an induction motor and then taking the output of the stator voltage and feeding it back into the field, and somehow they call this a doubly fed induction generator, and it magically gives them the ability to control voltage. I'm guessing some of you in this room understand that better than I do, but the point is, this is a technology that gives you the ability to control voltage some more. But the actual generator itself is directly connected to the grid through an AC feedback. So what you'll see in the models that I show in a little bit, where I'm more in my element, is that there are parts of it that are modeling the blade and modeling the generators swinging, and so there's more feedback between the mechanical and the electrical system. When you go to type 4 wind turbines, at that point you have an inverter that's taking whatever electric signal you're creating on the wind farm, running it through a full power electronic converter and creating an AC waveform. So at that point, whatever your source of energy is completely isolated from the grid. So the models actually get much simpler with the type 4 wind turbine, because we're not going to model the stuff on the mechanical side at all. And at that point, a solar plant, a battery, any device that's hooked up with a full converter like this in a transient stability tool is going to look the same. So all new wind farms are type 3 and 4 at this point. So. All right, another issue with wind turbines, there are rules about, I think these rules have been misinterpreted. There are rules about when you are not allowed to trip. That's what they're supposed to be. And they're saying that if the voltage drops below this value for this amount of time, as long as you're up here, you're not allowed to trip. I think you guys have figured out, I think some of the users in our space were treating this as I have to trip if I'm on the other side of this curve. So I think some people were modeling putting these curves in and just saying they must trip, but they don't actually have to trip. It's okay to keep operating and keep holding the grid up, hang on until the fault clears, and still be there. So these are rules about when you are not allowed to trip, not about when you have to trip. All right, just try to get ahead to. This is just going through the. This right here is the wind speed, I think. Is that right? CP. I always forget. I always look at this and go, this isn't in the model. Basically, all of the models that we use in transient stability make the assumption that the wind turbine is catching the maximum amount of power as it can all the time. These are curves related to as I change the pitch angle and as the wind speed varies, how much power do I get? So I think this is wind speed, and this is how much power I can get, and this is at what pitch angle. So depending on the wind speed, you end up varying the pitch angle to get the maximum amount of power. And none of our models do that, yeah.
Yeah, Jamie, I think the previous slide, I think, defines land, at least as a label.
Is the
It's
tip,
tipped to speed and speed.
okay, so it's related to wind speed. It's a normalized wind speed depending on how long the blade is.
Oh, I'm sorry.
It's the ratio of wind speed to blade length. Anyway, I'm kind of skipping over this because once you get to the transient stability models, we're not modeling any of this stuff. So what do these models look like? When you're on a Type 4 wind turbine, this is a Type 4 wind turbine. At this point, we've got that converter. So a lot of these turbine technologies, from what I understand, they may have a permanent magnet, synchronous machine, it could be anything. The point is, it's really up to the technology of the hardware folks. And because it's going through a converter, we just don't really care on the transmission side. Just creating energy somehow. All that we're going to care about is the control system that gets wrapped around this. And that's what we're going to model. All right. Solar panels, this is another big area of growth. There's kind of two different types of solar uses. One is on people's roofs, and the other is in a farm field next to a substation or nearby. So it's like more, do I have 10 panels on my house, or do I have 1,000 panels out in the field somewhere? And that is definitely growing a lot. This is a picture of where are good places to put solar panels. Is there a lot of it going up here?
More than you think.
More than you think, but there is. Yeah, it's the same in Illinois. You're about the same as us in Illinois, and that would be the answer for me too. It's when the government pays for 30 to 40% of the installation, it's more palatable. But most of it, when you talk to utilities, it tends to be Arizona and the Southern California folks. I mean, that's who's seeing it the most of it. This is a picture of the whole world, lots of places. It's funny, I remember talking to a customer in Abu Dhabi once about wind turbines, and or not wind turbines, about solar panels, and the biggest problem for them was sand. And it covers up the panels. It's like they have to go out and clean them off all the time. So it just depends where you're at. I mean, it's funny. You look at Germany. Germany is where the biggest installations, percentage-wise, are, and it's not even necessarily a particularly great place to put solar panels. So this is a plot over 2008 to 2015 of how much solar generation there is. So I mean, you can see summer, winter here, but it is growing a lot. That's still not a huge amount yet. I like this figure. This is a plot from got off a website of how much output there was from a solar panel. I assume this was like, sunrise to sunset. But the point is, there are a lot of clouds going by. So they're up and down a lot. So if you look at one solar panel, it's going to look very noisy. The assumption is if you had thousands of them in a subdivision, the clouds aren't covering all the panels all at once, hopefully. But
And Jamie, a good thing to point out about that image is it's from a grid storage company.
oh, that's true. What's that?
So they like
Yeah.
it.
This is, come by our batteries, is what is being said right there. All right, distributed PV, I talked about yesterday of how we model that with the load. It feels like there is the ability to have a lot more voltage control down at the house right now that's not being used at some point. I mean, most of these panels just try to do no harm, essentially. But people are starting to at least tell them, hey, you can't be absorbing lots of Rs, but they aren't being asked to provide voltage control yet. But eventually, who knows?
Anywhere?
Not that I'm not aware of any. Is anybody aware of? I don't even know exactly. It'd be the communication system to like talk to all the turbines. It's like maybe Verizon could get in that business.
Yeah, the 5G network.
Yeah, exactly.
That'll do it. It's gonna solve all of our problems.
Could you just do it off the terminal? Start supplying bars with the terminal?
You could, yeah, have everybody have a set point, but throughout the day, that set point, if you were trying to hold it here as the voltage went up throughout the day, you'd be absorbing bars and it'd probably be futile to keep it fixed at something. All right. Yeah, this was, again, some of you know this more than I do, but there was a fire in California, the Blue Cut fire, and a big part of the problem with that is in the original wind or solar panels put in, the manufacturers were being told you need to, drop offline if the frequency drops to here or voltage drops to here. So they installed all these panels that had all the same settings. So then, when an event happened and a whole bunch of generation got tripped and the frequency dropped, then a huge amount of load all saw this frequency drop and all left at the same time when they didn't really need to. And I think they ended up with an over frequency event in the end. Is that familiar to people? They had a big gen trip, but then they lost way more load than the gen they had tripped, and that was the problem. And that's where all of the momentary cessation stuff came from. It's like that the panels did not need to do that. They could have stuck around, but they were being told to trip, so they tripped. So the newer IEEE standards, I think from 2014, have changed those rules. And basically are telling us, hang around as long as you can.
Maybe?
Yep.
You said you have something that says this is a key safety requirement. Could you just elaborate on that for a moment?
Well, I think they're worried about fires on a rooftop. They want to, if the voltage or frequency is going too high, they don't want to start a fire, would be my assumption. Is that what you're thinking?
Well, if your house blacks out and your solar, it's like you lose the grid, okay, and your solar keeps on working, it's back feeding the transformer.
Okay.
Oh, okay.
So you're energizing the high side. It's like going into your house and saying, hey, I've got a generator, let me plug it into an outlet so I can just distribute it around my house without a disconnect switch. You're back feeding, and if there's somebody working on that distribution circuit, you can kill them.
Okay, all right, that makes sense.
So
I
you
didn't
gotta
think-
make sure these things trip off, and they do. I mean, that's the whole standard idea.
But if the dip is for 30 seconds, the crew's not going to be out there that soon.
Right.
So you can stick around for a while. Yeah. Okay, that makes sense. Thank you, Tom. All right. Now I got to the stuff I feel like more of an expert on, which is how to model these things. All right, so what happened with these models, say in about 2008 or so, is it's new technology, and all of the wind turbine models are coming into software tools like ours as user-written models. Because honestly, people are just learning how to model these things in these tools. And as you guys know, thankfully in WEC, you're very resistant to that because it's kind of a nightmare for you to manage and figure out what's going wrong when there's some black box code running and you don't know what it's doing. So in about 2010 or so, the WEC MVWG group got together and started creating what we call the first generation generic models. So this up here was the first generation renewable wind turbine model. And we already had a whole software set built around machines, exciters, governors, and stabilizers. So we just tried to create a model that mapped to that. So we have a machine I'll talk about in a second. We have an exciter So your brain should be going, you don't have an exciter on an electronic converter. That makes no sense. So in simulator, we call it an exciter, but it's really the electrical control for the wind or renewable plant. We then had a governor, which again, it's not, there's no shaft on a solar plant. So it's not like a typical governor. So governor really just means all the mechanical stuff. And then the stabilizer on the Type 3 was actually a pitch controller. So it was the thing that looked at the frequency and power and would vary the pitch if the frequency was going up. All right, the first generation, the problem with these models was it was people like PSLF and me and PSSE and folks at EPRI designing these models, which is great. We write good software, but we don't know how the hardware works. So we're just kind of guessing. So having done this long enough, I've accepted the fact that the only way to get a good model is to make a crappy model first. So that's what we did. We put out this Type 1 model, and then it had some ability to do control features. It was out there for 3 or 4 years, and all the hardware guys were like, those suck, they don't work, and they didn't work. So what happened was we made the second generation models, which worked much better. So what was different was, this is the Type 3. Mostly it's just extra control features. So there's extra stuff up here that I'm going to walk through in a moment about how we control the torque on a Type 3 wind turbine, and then looking at voltage and bars and power on any renewable plant. And we renamed the models. When we made the models in 2010, solar wasn't that big of a deal yet. So we were naming the models WT. And so there was like a 4-year period where people would call, how do I model a solar plant? It's like, oh, you put in a wind turbine model, which was confusing to people. It was perfectly appropriate. So we renamed the models into renewable energy generation converter, renewable energy electrical control. This stuff is only related to wind turbines. So we included those down there. And then this is a wind turbine torque controller. But then the plant controller, again, is generic for all solar, battery, whatever. I'm going to walk through these models in just a second. The Type 4 wind turbines were like this in the first generation. And then we added the plant controller. The solar model, you end up using these same pieces. I think the folks here know this, but when we made our renewable models, again, this is the problem with having software people do stuff, because we don't know how the hardware works very well. We assumed that the solar panels were simpler. So the REECB model I'll show in a little bit it's a simplified version of the REECA model, where we stripped out about half the input parameters so that you don't have to deal with them. And we were like, oh, solar panels don't need these. We were wrong. They need them. So you shouldn't use this model. You should use the A instead. All the things related to the momentary cessation are important in the solar panel. So. Energy storage, I'll show that in just a second. So the software implementation of this is you ended up with 3 new types of models. So inside the simulator, let me just go to the dialog here. So when you're on a generator dialog and you go to the stability tab, you have models, or machines, exciters, governor, stabilizer, and then you come under other. And the other, it's like just all the other models. And so there's various types of other models. There's aerodynamics, there's over-excitation, there's a plant controller, there's a PREF controller, relays, and so forth. So we just added in some new categories. The plant controller and the PREF controller were new for the second generation models. Yeah, and you see them inside simulator when you're looking at the models, and you go to other, you get different folders of other models in here. And, you know, you guys are GE users, so you're fine, but, I mean, you'll see things where there's like an REPCA and then an REPCA1. Those are the exact same model. It's just one's in GE and one's in PSLF. And Tom and I, over the years, have just kind of given up. I always say every engineer knows that the tool that they use always gives them the right answer, because otherwise they wouldn't be using it, and they're, right? So we've just been like, all right, we need to give them a model that's got the same name as what they're used to. So even though they're identical models, they have different names, so that PSSE users see their correct models, and PSLF users see their correct models. All right, this is a table, and actually if you go into PowerWorld's website later, and you go to powerworld.com/webhelp. That's our help documentation on the web. If you scroll down over on the left to transient stability add-on and overview, in the overview there's an entry here on renewable energy models. And it's got this table that's kind of telling you, depending on the technology you have, here's the models you should use. And then all of these models have grown out of the WEC community, and there's actually links to kind of the papers from 2012 to 14 on that. They're on our website. I don't trust WEC not to move it on their website. so I just downloaded it. Will be a permanent part of our help. So let me walk through these models so that you are familiar with them, because all the new generators you get are these models. All right, yesterday I talked about this low voltage thing and how this isn't really, this is for software. So the hardware people don't like it, but it's an artifact of how the software works. All right, calling this a model, having worked with it now for 10 years, I laugh. This is not really much of a model. Okay, what this thing is doing is, go back to that slide before showing the signals. So we've got this renewable model I'm about to talk about. All right, there's a control system over here that's sending over a signal that says, I want this much real and reactive current. And that is all that this machine is getting. And then coming out of it, it's telling the network, here is how much real and reactive current I'm giving you. So this is supposed to model the power electronic converter. So let's go look at that model and make fun of it. All right, the fact is that the power electronics stuff is going on at tens of microseconds. It's like 1,000 times faster than we're simulating. So all our model does is it says, I want this much reactive current. And it says, with a delay of 20 milliseconds, it magically creates it. It's two delay blocks. That is all this model is. We're not modeling pulse width modulation and point on wave stuff. It's too fast. We can't model it. You have to do EMTP stuff to do that. So you just put in a delay block. This is the same as a delay block. You have an integrator with the feedback subtracting. This is the equivalent to a delay block. So it's just showing, it's mostly drawn this way to make it easier to show there's a rate limit on it that says it can't go up faster than a certain rate. So that is all this is doing. There's then a little bit of a feedback that says when the voltage drops, the amount of real power will drop. That's what this lookup table is right here. And then this right here is related to, you guys have run studies. I started to talk about this yesterday. You see this all the time, and about every probably at least every 18 months at a WEC meeting, we have to spend half an hour talking about this again, because there's new people in the room. But when you run, I look at like the voltage at the terminal of a wind turbine. A fault happens, it goes down, and you always get these spikes. This spike here, and that spike can go quite high. All right, that spike is occurring because I have a fault occur. The control system is going to look at that fault and go, oh, I need to pull the voltage up. So if you go look at the renewable model, the electrical control, we'll look at in a second, it's going to push that up to the maximum desired reactive current, the maximum possible reactive current. And it's going to be sitting right there. And that's going to go through a delay of 20 milliseconds or so, which is about 5 time steps or so, right? That's fine. It comes in here, the voltage collapses. This stuff does some magic to push the current down to 0 because the voltage is 0. That's all fine. We go through the fault just fine. Then suddenly the fault recovers, or clears, and the voltage goes from something close to 0 up to say 0.7 or 0.8. And now this signal here is still coming in as maximum current, maximum reactive current, but now the voltage is recovered. And so it's going to push the voltage way high because it's asking for maximum current when the voltage is recovered. And the problem with this model is we're not modeling every 10 microseconds in the power electronics that we go, oh, voltage recovered, I should back off now. That's not in our model. It's too fast. So if we didn't do anything for about 4 or 5 time steps, we might hang out at like 1.6 per unit voltage or something. And it's just because it's not responding quickly enough. And there's nothing to do except throw up your hands and use EMTP and PSCAD tools. So, yep.
Why is the time delay 20 milliseconds?
Just to kind of smooth out stuff. I mean, you could make it smaller, but if you didn't have any time delay, then you'd create your own numeric. Yeah. And there is some time delay in there. Yeah, I mean, I don't know the control systems of the converter, but I'm assuming they're detecting faults and doing special stuff, and they're detecting fault clearing and doing special stuff. But I don't know that for sure.
Okay, but if we had it just as instantaneous.
If you had it as instantaneous, there's still a little bit of delay over in the even the renewable, even in the electrical control. So there's still going to be a couple time steps where it responds, right? Yeah. So to fix this problem, again, we have this thing that says high voltage reactive current management. Again, what it should really say is software fix so that we don't have these big voltage spikes. And so what it says is if the voltage goes above some threshold, it's going to try to just it's going to suck extra bars out for a few time steps just to pull the voltage down to clip it to some value. So if you look at a simulation, when you have the fault happen, where's voltage? Here it is. It goes down like this, and when the fault clears, you get this spike right here. You guys see it in PSLF. You see it in PS. I mean, all the tools do it. Huyan used to be with EPRI told me he talked to a converter person once who said, if you go look on an oscilloscope, you'll see a spike too. It's just shorter duration after a fault. Right? I mean, it makes sense that it's there. So anyway, what we do is, this is what I just talked through. In simulator, there's a parameter that will say, what is the maximum voltage? And so if you zoom in on that, basically we're just clipping it at that voltage, and we're doing that by just sucking bars out to bring the voltage down. And it, happens over about 20 milliseconds. 0.02. So I bring it up because I don't think this really matters that much, but it is confusing to new people looking at it, right? You guys think it matters? Or you're just
Well, if
used to
someone's
ignoring it?
joking on it, we can help them understand what's going on.
Yeah, it's a numerical problem with the kind of tools we have written. So we're just trying to get around it. All right, another choice, a new model that we're working on is called REGCB. And it's similar in that it has the two delay blocks up front. But then instead of taking these two currents and saying, I want this current, they're running them through an equation to create an equivalent voltage behind an impedance that's given. The user tells us what gives us a source impedance. And then we create a voltage instead in the algorithm. And the hope is that this gets rid of these voltage spikes. And we're testing this with EPRI's helping us test it across software tools. I'm a little pessimistic. I think we're going to get rid of the voltage spike, which is probably good because people mostly look at voltage. But if you look at current, you're going to see a spike there instead. But people don't look at current, so they won't notice it. So we just traded one problem for another. But I'm not sure. We've just started playing with it. The C model is another one we've coded, but no one's using it yet. All of these converters, they're trying to really create a voltage that's a certain phase, out of phase with the terminal voltage, which means there has to be a phase lock loop trying to figure out what the phase is. And usually that is very, very fast, and we don't include it. This predates my working in this, but I think in like 2008 or so, all the user-written models people had included this phase lock loop that was really fast. From the old guys who are now retired, tell me it was a huge pain and caused all kinds of problems. But we're reintroducing it again. So we'll see. This will be another choice. So these are beta models. All right, so let's get to the electrical control. This is the electric control that you're going to see on solar and wind plants. All right, the first thing to do on this is to go, it's not as, just tell yourself, it's not as complicated as it looks. The reason it's not is because there's a bunch of flags. The blue values, there's a flag here, a flag here, a flag here, and a flag down here, and one over here. So depending on how you set these integer flags, this model gets really simple. So for instance, if you were just doing, I want it to stay at constant Q, and just stay there, people would come in here and they'd set this Q flag to 0, and then all these PI loops here in the middle, and this complication just, it's eliminated because you're going around it. So, and then you're just coming out the other way, looking at the plant controller coming in from the green values. So when someone gives you a model, they have to make a choice as to, am I controlling voltage, current, constant power factor? You can do constant power factor over here, where you're looking at P, multiplying it by the initial power factor, and then feeding in that I want to stay at constant power factor. It's another thing you can do with this model. On all these models, what you're going to see in the power flow you're going to tend to see something that looks like this. Where this is, say, 230 kV, this is, say, 34 and a half. Is that about right for your distribution feeder networks?
Mhm.
And this is like, I don't know, 460 volts or something. So I guess I should say 0.46 or something kV down here. So what you're doing is you're modeling the transformer at the point of interconnection. Remember that whole tree mess of wires going out to the hundreds of wind turbines? That's modeled by one equivalent branch. So somebody had to come up with that equivalent. This is the transformer mounted at each wind turbine, right here. And what's gonna go on with the REEC model is it's gonna be looking at its terminal. So it's doing the local control, trying to control the constant power factor here or voltage here. It's right there at each turbine. That's what this is meant to represent. And depending on how you set the flags in here, you get voltage or constant power factor. And then up on this path, this is more kind of what I think of as the emergency quick control. So it's saying if the voltage suddenly drops with some gain, start pushing out lots of reactive power right away. That's what this stuff across the top is doing. And then down along the bottom, this is the real power control. So that it's got some reference power coming in, and then again a delay in the control system before it feeds it off to the other side. So right here I've got here's how much power I want, here's how much reactive power I want, and then at this point there's a total current limit on this thing. So that is modeled right here. And then the user makes a choice of, all right, if I'm asking for too much current, do I want to get rid of the reactive power or the real power first? Which one's more important to me at this plant? So you get to pick a flag that says, get rid of real current or reactive current. So if my maximum current is, say, 1.2 per unit current, and I'm asking for 1 per unit power and 1 per unit reactive power, then that's going to be like 1.4 per unit total current. So the question is, do I back the P down or the Q down first? Who goes away first? And that's this choice you have to make as a user, whoever gave you the plant. So this model is really used for all the renewable plants. Anybody, I mean, I know it's ridiculous that, hey, I just showed you this for 2 minutes. Do you have any questions? Go ahead.
I was just wondering that voltage spike you talked about earlier, they probably debated it a lot at model validation groups and stuff, but.
Every 18 months, at least for half an hour.
Isn't that one of those things you just throw into the cache? Is too high speed, so you just assume it doesn't, like, can't just give it a bigger time constant and let it filter out?
Yeah, I mean, Hamodi's right. If we make that other time constant smaller, it could go away quicker.
Or it would go away quicker, looking
But
like the.
that would then cause other problems. So I mean, I think what's going on is the converters have slow, tens of millisecond base control, but they're also smart enough during sudden weird events like a fault or a fault clearing that there's special control going on, and we just can't model it. So this is our vain attempt at doing it, and then we just kind of have to keep telling our users over and over again, ignore that, ignore that. It's kind of like the hash marks that happen when the network equations don't solve. You guys get used to going, oh, that was weird for a couple time steps in there, but you ignore it. Same thing, just ignore this. All right, one thing with this model, when it was made, we were building it for wind turbines. So we're like, you can't absorb power in a wind turbine. You can't suck in power. So we just hard-coded the minimum reactive power to 0. And that was great right until somebody wanted to use this to model a battery. And then we're like, oh, crap, we can't charge. So RECC, it's literally the same as A, except for the red stuff down here. Basically, it says that the minimum current is the negative of the maximum current so that it can charge, so it can absorb power and charge up the battery or flywheel or whatever. I can say I lobbied hard for us not to include this stuff down here because I think it's silly. It's modeling the state of charge of the battery so that you can say it starts at half of the capacity of the battery, and it takes 30 or seconds, or actually, who installs a battery that only has enough storage for 30 seconds? That's the whole point. No one does that.
Hopefully not.
So usually this time constant here will be like 3,600 for an hour or something. So then, but it's cool, you can keep track of the battery charge, but you're never gonna hit the limits in a stability study, I don't think. But you could, you can model it here. If it
Wanna
only
know
had,
how much you use up.
yeah, it had 10 seconds there. Once it hits the min or max charge, it basically makes it so you can't create power or you can't absorb power, depending on which limit you hit.
Could be a why there.
Well, okay, if you only had a shorter period, okay. But even then, it's like, you as a user would probably go, let's assume you run it for 10 seconds and then you run out of power, so you just trip it. That would work too. Huh?
I don't know what the duration of the batteries are, but I thought some of them are used for frequency regulation, so that, for your conventional units, they weren't constantly sort of being bumped up and down.
Okay.
I'm not sure if it's 30 seconds or a little bit longer.
Okay, well then you could use this for that in the renewable environment. But that's what this is for. You would use this, any storage device with power electronics. Okay. There's also a D value. One of the things that I make jokes about lookup tables. In the A, B, and C versions of this, there are 4 points. I think on the VDL, maybe it's 5. This is just a piecewise linear curve that says, as the voltage goes down, the maximum current goes down, or something like that. There's like some, I max for real power versus voltage. So the user can put in a piecewise linear curve for that. All right, so they have about 5 points on here. The hardware manufacturers are like, we can't get by with less than 10. So the D version that we're working on now is the red parts are new, but the big part is that there's 10 points here. The problem for you as a user and me as a person who supports you is that's 10 piecewise linear points on 2 curves. That's 40 input parameters for you to be puzzled by. But they're all right there, so you can model this in greater precision. So, all right. This is modeling the interaction between the turbines on a Type 3 wind turbine. I mentioned that there's feedback between the electric and mechanical system. So this model lets you put in how much inertia is there on the actual machine itself that's in the heart of the blades, and then how much inertia is there on the blades themselves, kind of model the blade system as one inertia, and then you can have it kind of oscillate back and forth and see that if you include this model. It's never clear to me how important it is. Dimitri, you have any? It's like so the mechanical people can see that it's oscillating and think it's good.
The data is suspect too.
The data that gets put in it, yeah, because I think in the end it doesn't really affect the transmission system that much. So, but it's in there anyway. That's the pitch control. This is for Type 3 wind turbines where it's looking at the speed and the power and might be changing the angle of the pitch on a Type 3 wind turbine to prevent it from going over speed and braking. And then this model had some max and min angle limits on these different parts of the block diagram. And people always want more. So the B version of this, it's identical, except we've got different limits all over the place. So it's just more input parameters for people to mess up is kind of how I think of it. That's there. This is a torque controller that's on a Type 3 wind turbine. I want to just finish up and get here to the renewable model, the plant controller. So everything I've been talking about so far. So we had an REGCA, we had electrical control, there were some various torque control, forget the names, but there's some other models here. And finally, we have a model called REPCA. All right, all of these models are looking local. They're looking at the local control of the wind turbine. This is the plant controller, so this is the guy that's going to be looking out at the point of interconnection. So this is the guy where you have to say, I am regulating at the plant level. Now let's say it's regulating this bus. And I am regulating the power flowing in here, and the reactive power, and also current matters in here too. So as part of the input parameters for this model, you have to give it a branch and a voltage bus, which is one of the terminals of the branch, where the plant is measuring voltage and power, and then has to be sending with telemetry that data back to all of the individual wind turbines. So this is what the REPCA is looking out there. And then this guy, it's got some, as Tom said, some phase compensation on a lead lag block. It's got a PI loop. It's got a PI loop down here in the P. So this is kind of the control system model for it. And then everything else is, what is it measuring? So you've got these flags. If I wanted to regulate to constant, or if I wanted to try to keep the reactive power out here constant, then I would come in here and I would set this ref flag to 0 to send the signal down this way. So I'm coming in here, and now I go this way, and I'm going to be measuring the reactive power on that branch, comparing it to where it starts, and running it through a deadband. So if I move just a little, maybe I don't respond. There's an error min-max, run it through a PI loop, and it's going to be driving this value to 0, trying to bring it back to where it started. So that'd be for constant Q. If I wanted to be regulating the voltage right here, but I wanted to kind of regulate back behind it, that's like droop control, where you're not regulating out into the system, but back behind. In particular, I might do that if I had a second wind turbine. If I had a second wind turbine at the same point of interconnection, if both of these guys try to regulate that voltage together, they're going to fight with each other. So if I set it up to regulate a little bit of an impedance behind it, so that instead they're regulating here and here, then they're not going to fight with each other. So in order to model that, I set this ref flag to 1. I come this way, and if I want to do reactive current droop, then I set the V comp flag to 0, and I go this way. And so now I'm regulating that voltage plus, no, minus. Oh, wait, let me look here. It's an error on the block diagram. The pluses and minuses aren't there. I'm pretty sure it should be voltage minus. Q times Kc, so that as the reactive power goes up, the voltage set point goes down. So you're going to be regulating kind of against a curve like this, where as the voltage goes up, I want the Q to go down, and gives you a little bit of a droop control. And I'll talk about that this afternoon, even in the power flow. So this is just all depends on what the wind turbine's doing. One of the things I don't understand, maybe you guys do, does the control strategy of a wind turbine change, like seasonally? Okay, good. I always worry about it. And the part along the bottom, this is for the real power control. Most things I've seen in any commercial case, this freak flag is set to 0, and there's no power control. Is that your experience? Anybody doing that yet? So eventually, you can, even a wind turbine, it can't, obviously, you're not gonna operate a wind turbine like 10% lower than its maximum power, like all the time, just in case, because that's very wasteful. But certainly if the frequency goes high, the wind turbine could respond and drop. Right now, none of them do in your simulations. If you wanted them to, or if you're thinking about asking them to, essentially, you'd come in and set this freak flag to 1, and then you'd come down here and tune, this is the droop going down or the droop going up. So the droop going up, you'd probably set to 0 because you can't go up, the power can't go up. But the droop down, you could set to something, and then it would provide the governor type control with the wind turbine. So that's in the model, although no one uses it right now. So, all right, and I'm going to have a whole presentation on that later. Last thing to bring up, what if I had this situation right here, where I have 2 different wind farms that all kind of come into the same substation. It might make sense to just do droop control that's completely separate from one another. That works fine. What if I wanted to not do that, though? What if I wanted to regulate this power instead? If I'm going to do that, I cannot have these do this independently because they will fight with each other. So I need to put in a special new model called REPCB, where you have one control objective over here, but your outputs are going to more than one generator. And in simulator, we have REPCB, where we let you go up to 50 generators. And we have REPCB 100 because the customer begged because they had 60 they wanted to do. But I don't think anybody's doing this yet, but over time I think it will happen because you'll have a wind farm with type 3 wind turbines, and then 15 years later they'll come in and add some new type 4 wind turbines that are all controlled together, and then this model is going to be needed. Do you guys have any systems like this right now? You do? Okay. It's like, could be an SVC also being controlled. So, do you use this model yet, or no? Yeah. Okay. All right, I'm going to hand it over to, well, does anybody have any other questions about wind turbine models?
Like Jones Canyon, that would be an example. We have all the wheat field and Pebble Springs and junipers.
Jones Canyon, I think, are type 2 wind turbines, though, aren't they? Huh? Oh, they're both? Yeah.
Horseshoe bend.
Or the
All right,
stack
you ready?
stuff.
Sure.